All right, welcome back. So, set theory. Okay, so we are looking at set theory in this video tutorial. Okay, so now let's start by defining the term set. Okay, now those set definition can be of different, you know, okay, perspective. But in mathematics, we define set as the collection of well-defined objects. So a set is a collection of a well-defined objects. Okay, for example, when you actually okay, when you mention set of numbers, so it simply means that the object of that set will actually include all all numbers. Now each object in a set is called the element of the set, so please take note of that. So for example, now if I say set of numbers, right, or set of integers, now this is how I actually okay uh write set or denote a set. All the element of a set is being enclosed in a braces. Okay, so this is set of integers starting from one. That's 1, 2, 3, 4, 5. Okay, 6. Then I can stop at this point, or I can actually continue. So which simply means that the element of the set is actually being written inside the braces, and they are being separated by comma. Okay, so each element is separated from each other by a comma. So now, so these are the object of the set, and at the same time they are the element of the set. Okay, so the object of a set is also known as the element of the set. Okay, so now you can also, apart from calling it the element of it, you can also call it a member. For example, now if I say that 2 is the element of this set, okay, I will write it this way. I will simply say that 2 here is a member, or 2 is a member of set A. So this is what this. So 2 is a member of set A, or the element of set A. So this is how we represent the member, okay, of a set. So I hope that is well understood. Okay, so as usual, you know what we normally do. We actually look at the basic concepts, okay, that is used to that's used to describe a particular topic that we are looking at. So we are looking at the basic concept that is used in describing a set. So we start one after the other. I've already mentioned some few. For example, if I have A, okay, let's say A is a set of alphabets. A, B, C, D. Okay. Now, of course, um, A, B, C, D is the element of A, and this found inside the braces. Okay. So one basic concept is the concept of element, which I've told you. So I can use this symbol. Okay. A is a member, or the element of small letter A is the element of A. Okay. So this actually represents that if that A is a member or even an element of set A. So please take note of that. But since this particular set doesn't have E, so if how do I say that E is not a member of this set? So all I just need to do, I use this as symbol, but I'll have to cross it. I'll simply say that, okay, E is not a member of A. So that is how we actually show that an object is an element of a set, or is not an element of a set. Okay, so now the element of a set already know, okay, are separated by commas, and they're all enclosed in braces. Please take note, it's not brackets. So there's a difference between braces and brackets. You should take note of that. Okay. But apart from actually writing out outrightly the element of a set, okay, and enclosing them in the braces, there's another way of writing the element of a set. Okay. Apart from writing it out inside separated by a comma inside the braces, there's another way of writing it, and that's other way of writing it, okay, is what we're going to be looking at. It's known as set builder notation. Set builder is another way of writing out the element of a set. Okay, so now how do we use the set builder notation to write out to express the element of a set? Now, in set builder notation, we are not actually expressing the elements of a set outrightly by actually separating them by a comma, okay? But we are going to actually write a definition. So in which, from that definition, someone who actually sees the definition, okay, interpret the definition, and of course, from the definition of the set, then the person can now write the element of the set. For example, let's say this is set B, okay? Now I want to write the element of this set B by defining the content of set B using the set builder notation, okay? So I'll now go this way. Set B is actually a set of X such that, so once you see this this symbol, it simply means that such that, or if you don't use this, you can use this, okay? But let's use the previous. So B is a set of X such that X is an integer. X is an integer. Okay, then I put comma. Comma simply, in set builder, we use a comma to represent and. So X is greater than 0. Then I now close my braces, okay? So this is a set builder notation, okay? We use this information, this definition to build our set. This doesn't actually, okay? The set builder doesn't list out the element, but gives you a definition which you can use to list out your element. So now let's go through this again. So this is B is a set of X, such that set X here is an integer and X is greater than 0. This simply means that, so if I should actually use this set builder notation to list the set of B, okay, I'm gonna start B is greater than 0 and then B is include integers, right? So I'm gonna start from 1. That's gonna be 1, 2, 3, 4. Now there's information that this set builder of B didn't actually include. It didn't include where I should stop. So since the set builder didn't include where I should stop, that means what I have here is going to be an infinite, okay? Infinite set. So I will just use dot 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 to show that it actually continues, okay, to probably infinity. So please take note of that. That is the set builder notation. Okay, let's proceed. Okay, so we're still gonna be, let's look at some other terms. Let's look at the equality of a set. When is two sets said to be equal? Okay, equality of sets. Now set A is equal to set B if they actually contain the same element, okay? It doesn't matter the order to which the element is being arranged, in as much as it doesn't matter whether it is actually being repeated or not. For example, let's if I have set A to be equal to, okay, a set of elements which of course include 2, 1. Now I'm now having set B, okay, set of elements which also include 2, 1, 2. But even though it is still being repeated, I have 1, 2, 1. So the important thing is that these two sets only have 2 elements, 2 and 1. So it doesn't matter how it is being arranged or number of times they are being repeated. So I can simply say that A is equal to B. Why? Because they contain the same elements. Okay. the same element. A is equal to B. So please take note of that. All right, the next term that we're going to actually look at is known as singleton set. Singleton set, okay? As the name implies, every singleton set will always, okay, contain just a single element or one element. All right? Every singleton set contains one element. Okay, for example, if set X is singleton, invariably now X is going to be equal to, let's say, -3, just a single element. So please take note of that. Okay, then the next term that we ought to know, ought to study is called an empty set. An empty set. Okay, now it's either called an empty set or you call it a null set. Of course, as the name implies, okay, a set is said to be empty if it doesn't have any element. And the symbol that we use for empty set is either we use this phi or we use an empty braces. Okay, an empty. So if a set is actually empty, okay, if that set is empty, we say, okay, let's say set A is empty, it doesn't have any element, we use this to represent that. So please take note of that. Okay, then we'll continue. Another term we need to also take note of is finite sets. Okay, a set is said to be a finite set when it actually contains finite elements. So of course it's a finite set. Let's say set A is finite. All right, if all the element is actually listed out, okay, and without miss, okay, indicating that the set actually continues. Of course, if I use dot dot dot, it simply means that the set continues. Okay, so this is finite because all the element has been listed out inside the set. Okay, and it has been inside the open and the closing of the braces. But if the set is infinite, then you know very well that it shows that the element of that, what the element that is listed is not all the element in the set. Okay, it continues then till infinity. Okay, the set actually continues to infinity. For example, if A is an infinite set, I can just go this way: 1, 2, 3, 4, then dot 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 dot. Okay, so I can even include infinity, so integers from 1 to infinity. So please take note of that as we proceed. Okay, so we are going to talk about subset. Okay, subset. So as the name implies, when something is a subset of another set, okay, if invariably that set is being derived from the other set. But now let's see how we actually define it. Okay, now by symbol, if I say that a set B is a subset of A, this is how I will write it. Okay, set B is a subset of A. What does it mean? It simply means that, okay, every element of A is also the element. Every element okay of A, okay, are also the element of B. So now look at how, if you look at this symbol, okay, that I use here. So I use the symbol set B is a subset or set B is equal to set A. Okay, so when you use this kind of subset, simply means that there's this tendency that B, okay, all the element of B is equal to the element of A, or in some cases the element of B might be less than the element of A. Okay, now let me illustrate this. For example, okay, if I have A to be equal to 1 comma 2 comma 3 comma 4, and I'm having B to be equal to, okay, the same 1 comma 2 comma 3 comma 4. Okay, let me close up. Okay, so though I can simply say that B is a subset of A, okay, then at the same time I can also say that B is equal to A. B is a subset, or the element of B, okay, is also the element of A, and there is no, the element of A is not greater than the element of B, so B is a subset, and at the same time B is equal to A. But a situation where, okay, let's say A now is having less one more element or more element than B. Let's say I'm having 5 now. Okay, then of course B is gonna be 1 comma 2 comma 3 comma 4. Okay, so B now is having less elements, okay, from than A. Okay, then I can simply say that B is a subset not equal to, okay, such type of subset, this is how you represent, is known as, so I can simply put it in words that B is, please pardon me, okay, I can put it in words that B is proper. B is a proper subset of A. Why? Because, okay, not all the element of A is contained in B, so proper subset. But this one is improper because they are equal. All right, so please take note of that. Okay, let's proceed. So we are going to be looking at what is known as universal set. Universal set. So as the name implies, and of course the symbol for universal set is U. Okay, so remember, every set must be a well-defined object. Okay, so an universal set is simply that set that contains all the elements under that particular definition. Okay, so universal set must actually have all the elements under the definition of that particular set. So which simply means that other set, okay, other sets under that definition, under that particular definition, okay, other sets are subsets. Okay, other sets are subsets, okay, to the universal set. So which simply means that universal set must be defined first. Okay, for example, if I say that, okay, universal set U is defined as the element X such that 0 is less or equal to X, and X is less or equal to 10. So that means this is the definition. That means you will have to carry all the elements under this definition. Okay, this is a set builder notation. So let's build U. U now is going to be equal to That means S will start from 0. Okay, so that's 0, comma 1, comma 2, comma 3, comma 4, comma 5, comma 6, comma 7, comma 8, comma 9, and then of course comma 10. Okay, so but if I now have set a subset, okay, it can be a subset. It's now a subset to the universal set, where I can say, okay, set A is actually x, such that, okay, 0 is less than x, less or equal to x, and x is less or equal to 10. Then now bring a clause, okay, let's say x okay, is, let's say, greater than 4. So you discover that now x now is a subset of the universal set. Why? Because A is a subset of the universal set. Why? Because A will now start from 5. Okay, A will now be 5, comma 6, comma 7, comma 8, comma 9, then comma 10. So all other sets, they are actually a subset to the universal set. I hope that is well understood. Okay, so so far so good. We are going to be looking at okay, basic set operation. The basic set operation. Okay, so of course that's going to be operation that involve union, intersection, okay, complement. So we're going to take them one after the other. So I'm going to start with the very first operation of a set, that is the union of sets. Okay, so I'll just I use two sets. Okay, the union of sets. So I'm looking at the union of two sets, and of course the symbol that is used, okay, to express the union operation of two sets is actually A. Let's have a look at two sets, A union B. Okay, now what is the union of two sets? Union of two sets is, of course, it's actually going to be a set, okay, that contains the element of either A or B, or even both A and B. Okay, either in the either A or B or both. For example, let's say I have A to be equal to 1, 2, 3, 4. Then I have B to be equal to 3, 7, 8. So if I'm being asked to find A union B, so I'm looking at the element that is this element, this set of unions is going to be set that is either here or both. Okay, they must be inclusive. So for me to actually list out the element, okay, of these two sets, okay, or possibly in a simple term, the element of both A and B. All right, but I will not have to repeat any element. Okay, so I can go in ascending order. Start with 1. 1 is found in A, okay, but it's not found in B. I go to 2. 2 is found in A, not found in B. Now I go to 3. Okay, 3 is found in both. I go to 4. 4 is only found in A. Then I go to, what next do I have? Okay, the next 7, right? Found in B only. Then 8th. So that's A union B. Okay. Number 2. Let's look at A intersection B. Okay. So this is actually a set of intersection. okay, of set. So invariably it's basically the intersection of just, let's say, two sets. So we take the intersection of, let's say, two at a time. Okay, so if I have A and B, okay, just let's say using this example that I have up here, the intersection is simply the element that is found in both, or the element that is common to both sets. Okay, so, and of course we use this symbol, okay, the symbol n, small letter n, okay, looks like n, but it has to be big. Okay, so now let's look at the intersection of these two. So what is common, what's the element that's common to A and B? And that's just 3. So it's a singleton set, just a single set. So that is intersection. So please take note of that, intersection. Now apart from union, can actually both union, intersection can, may not necessarily be uh just for two sets. Okay, it can go as many sets as possible. Okay, it can go as many sets as possible. So what simply means that if I'm dealing with intersection, I can do as many intersection as possible. If I'm dealing with union, I can deal with many union as possible. Okay, it may not necessarily be just two sets, it can be many sets. Okay, so I hope that is well understood. So here I'm going to be looking at the difference of two sets. Okay, so for example, if I'm looking at the difference of two sets, let's say I got set A, okay, to be equal to 2 comma 3 comma 4, and I got set B, okay, let's say 2 comma 4 comma 5 comma 6. So now the difference, the symbol for difference is A slash B. So it's something as saying A minus B. All right, so difference, that is A difference B, or invariably I'm subtracting B from A. So what does that mean? Okay, so if I should subtract, basically, okay, A from B, then okay, let's of course let's look at B being a subset of A. Okay, so I have to take away this, so I'm taking away this. So here we go. So now, so if I should subtract 2 from A, now subtract 4 from A, so what I left now is going to be A difference B. What I have left? So that's going to be, what I have left is going to be 1, then comma 3. Okay, so that is how you evaluate difference of two sets. So I hope that is well understood. Okay, those are basic set operations. Okay, now we are going to talk about complement, the complement of a set. Of a set. Okay, so now of course you know that we are told that every set, okay, universal set actually contains all the element under that particular consideration or definition. Okay, and every other set is a subset of the universal set. Okay. So which simply means that the complement of a set is simply the set, the element, okay, the set of elements found in the universal set but is not found in a particular set. Okay, for example, let's say you got universal set to be equal to, okay, simply let's say 1 2 3 4 5 6 7 8 9 and 10. So yeah, now let's say got set A to be equal to even numbers, okay, from the same range, in the same range, 2 4 6 8, okay, and 10. Okay, I believe these are my even numbers, right? So now if I'm being asked to evaluate a complement, I use this symbol A prime. Okay, I use A prime for complement. So this is the symbol for complement, prime. So all I just need to do is to subtract, okay, to actually subtract all the element of A from the universal set. What is left, okay, it becomes a complement. So those elements in universal set that is not found in A becomes the complement. Okay, so 1 is one of them, 2 is found here, so 2 is not a complement, 3 is not found. So invariably all the odd numbers, so that's 1 3 5 7, okay, then 9, so becomes the complement of my set. So I hope that is well understood. Okay, so we are going to look at what is known as this symmetric difference. Symmetric. Okay, symmetric difference between two sets. Now the symmetric difference between two sets, let's say set A and B, is given as A delta B. Okay. Now the symmetric difference between these two sets is actually the set of elements, okay, that is found either in A, okay, or in B, but not in both. So invariably now, I'm looking at the union of sets of the element. The symmetric difference is going to be the intersection, okay, of the element. That is A intersection B complement. What does it mean? Okay, I'm looking at set of the element found in A, okay, but I have to make sure that I remove the one that is in B inside A. If that makes sense, I'll also do that to B. Okay, set of the element, then I have to complement out A. So this is a symmetric difference. Okay, or invariably put it this way, you put it in terms of difference. All right, A delta B is A, the set of A, I have to take away B from it, then I now do the union of the set of B, I have to take away A. So A difference B union B difference A. That is symmetric difference. Okay, so for example, let's say you have A to be equal to okay, but let's say you have set A, let A be equal to 1 2 3 4 5 6, 1 2 3 4, then 5 6. I close my braces. Okay, then now you are now having B to be equal to 1 4 1 comma 4, then comma 5 comma 6 comma 7, then of course comma 9. Okay, so if you're now being asked to find the symmetric difference of A delta B, okay, it is just very easy to find. Okay, remember, the symmetric difference between A and B is simply the set of elements found in A or B, but the one that is found both in both of them definitely is not going to be a symmetric difference. Okay, so now I'm not going to symmetric differences. I'm not going to take one because one is found in both. I will take two. Two is not found in both. Two is only found in A. Okay, I'll go to 3. Yeah, I also take 3. 3 is not found in both. I won't take 4. 4 is found in both. Okay, both sets. I won't take 5. 5 is found in both sets. I won't take 6. 6 is found in both sets. But I will take 7, which is found in B, and 9, which is found in B. Okay, so this is just symmetric difference. Symmetric difference. I hope that is well understood. Okay, so these are basically so the basic concepts, okay, that is used in describing a set, and you should take note of them. Now, one thing about all these concepts is their symbols, so please take note. So go through the video again, because in examination, okay, the symbols will not be defined, will not be given in words. Okay, so every operation will be given by symbols, so it is left for you to actually interpret that symbol, know exactly what you're up against. Okay, so I hope that is well understood. So I will give you the opportunity to go through all the basic concepts and of course the basic operations. Okay, get to look at their symbol again and understand their symbol. Then once you are done, we are gonna be looking at Venn diagram in the next video. Right, see you in the next video. Thank you very much.